Hello, my name's Eleanor and I'm a PhD student at the University of Nottingham. Today I'm going to be presenting my research on the effects of long life exercise on motor unit properties across the deep and superficial areas of the vastus lateralis muscle. The term motor unit describes the motor nerve and the muscle fibres it innervates. Motor unit numbers decline in older age, and this contributes to reductions of muscle mass, strength and function. The compensatory process of motor unit remodeling enables the rescue of denervated muscle fibers via axonal sprouting and reinnervation, helping to reduce fiber loss and atrophy. A number of findings suggest that old master athletes are more successful at this remodeling process, displaying larger motor unit potentials, or MUPs, assessed via intramuscular electromyography, and fewer histochemical markers of denervation when compared to less active controls. Furthermore, data from healthy young has demonstrated that motor units are not randomly located within the muscle, with those located superficially larger than those located deeper within the muscle. Therefore, the aims of this study were to determine the effects of aging and activity level on the heterogeneity of motor unit properties across deep and superficial aspects of the vastus lateralis, or VL. We used intramuscular electromyography, or IMG, to sample individual MUPs from the VL of 83 males grouped into young controls, young athletes, old controls, and competitive master athletes. The characteristics of these participants are shown in Figure 1 on the poster. All MUPs were recorded during a sustained isometric contraction held at 25% of the participants' maximum voluntary contraction. A total of 1,414 motor units were isolated, with an average of 17 per person, from which multiple motor unit properties were assessed. The methods for this are shown in Figure 2 on the poster. Multi-level mixed effects linear regression models were performed on each group to account for within-subject variability and to determine the effects of depth on these parameters, with significance assumed when p was less than 0.05. So we found that motor unit potential amplitude, which indicates motor unit size, was larger in deep motor unit potentials from young, old, and young athletes when compared to superficial, but did not differ across depth in master athletes. Similarly, the near fibre MUP area from the fibres closest to the recording electrode were greater in deep MUPs from young, old, and young athletes, but did not differ in master athletes across depth. Motor unit complexity, represented by the number of turns in the MUP template, was also greater in deep MUPs compared to superficial ones from young, old, and young athletes, with no difference across depth in the master athletes. Graphs of these results are shown in Figure 3 on the poster. There is a heterogeneous distribution of motor units in VL, with deeper motor units demonstrating larger motor unit potentials. These are consistent across young and old people, but master athletes show a more homogeneous distribution of motor unit properties, similar across depths. These data suggest motor units of the VL are not randomly located within the muscle and exhibit a level of plasticity that is influenced by both age and activity levels. This further supports the notion that motor units have undergone greater levels of remodeling in master athletes, resulting in motor unit expansion and fibre reinnervation. Therefore, a greater level of age-related motor unit remodeling occurs in lifelong exercises. Overall, these findings indicate that maintaining activity levels in older age promotes motor unit remodeling and fibre reinnervation, which could ultimately be protective against the loss of muscle function observed with aging.